Here's the deal. Most vectors get spun around by a matrix. But one direction refuses to spin. It only stretches, same line, just longer. That special direction has a name, eigenvector, and the stretch factor, that's its eigenvalue. Watch closely. One direction survives, no rotation, just a clean stretch along its own line. See the gold vector pulsing? Stretch factor 3. Now how many directions survive? 1, 2, or infinitely many? What they are, how to find them, why Google ran on them. Let's make this concrete. Take the vector 2, 1 and hit it with this matrix. 2 and 1 across the first row, 1 and 2 across the second. Now watch the matrix act. The vector stretches and swings off its line. See that red arc? It measures the angle change. Both length and direction changed, and that's normal. That's what matrices do. Nothing stayed still here. No special direction yet. Now try 1. 1, same matrix. Look, it points the exact same way, 3 times longer, 0 rotation, no red arc, none. There it is, the eigenvector. The direction that survives, only stretched, never rotated. And here's where people mess up. How do you find that direction without trying every single one? There's an equation for that, don't worry. But first you need the full picture. Every vector all at once. Most vectors rotate 1 survives. Hold on to that contrast because now we zoom out and watch every single vector at once. Now let's zoom out and see the whole story. Every arrow on screen is a different vector. Every direction you can point from the origin. Now the matrix hits them all at once. Watch, almost every vector twists, rotates, changes direction. The whole space is moving. But this one, look, no rotation, no twist, it just stretches, everything else fights. This one is perfectly aligned. And it's not just one vector. The whole line through the origin. Every vector sitting on it survives at any length. Now here's the strange part. Change the eigenvalue. 3 triples it, 1 leaves it alone, a half shrinks it. Same direction every time, only the length changes. A big number stretches, a small one shrinks, and that number? That's exactly the eigenvalue. Now sweep the eigenvalue from 3 down to -1. At -1, watch the vector flip to the opposite direction, same line reversed. Negative eigenvalues don't break the rule, they just reverse it. The eigenvalue sets the length, the eigenvector sets the direction. That's the whole idea right there in one frame. But seeing isn't the same as finding. How do we actually compute these without checking every single direction? Here's the equation. AV equals lambda V, that's it, 3 symbols. Master what each one means and you've got the entire idea of eigenvalues. A is the matrix, the transformation. V isn't just any vector, it's the special one. Lambda is just a number, a plain scalar. And this equation does more work than you'd think. It powered Google's very first search engine. Keep it in mind. First though, what's it actually saying? Before we go further, meet the identity matrix. 1, 0, 0, 1. It leaves every vector unchanged, same as multiplying by 1. I times any vector is just that vector. I times 2, 1 gives 2, 1. In a minute, this is the key to the whole derivation. So here's what the equation says. Apply A to V and you get the same thing as just scaling V by a number. No rotation, just stretching. Look, side by side, AV and lambda V. For an eigenvector, they land exactly on top of each other, same arrow. 2 descriptions. 1 warning, not every matrix cooperates. A pure rotation twists every vector. No survivor, so no real eigenvector. By real, I mean ordinary numbers, not complex ones. Our matrix is symmetric. The entries mirror across the diagonal, and symmetric matrices always have real eigenvalues. So which V and which lambda? Finding them is clean algebra, but first 2 tools. Everything so far was pictures. Now the arithmetic behind them, 2 tiny tools. And I promise, numbers, not magic. Tool 1, how a matrix acts on a vector. Take each row, multiply piece by piece, then add it up. Here's our A, 2, 1, 1, 2, and V equals 2, 1. 2 times 2 plus 1 times 1, 5. 1 times 2 plus 2 times 1, 4. So A sends 2, 1 to 5, 4. That's the rotation from the very first frame. Now the golden vector 1. 1, 2 times 1 plus 1 times 1, 3. 1 times 1 plus 2 times 1, 3. It lands on 3, 3. Exactly 3 times itself. The whole animation in numbers. Tool 2. The determinant. Start simple, a 1 by 1 matrix. Its determinant is just that number. 1 keeps everything, 0 squashes everything to the origin. For a 2 by 2, the determinant is 1 calculation, A times D minus B times C, take the unit square, hit it with A, and watch it turn into a parallelogram. The area of that parallelogram, that's the determinant. Are A 2 times 2 minus 1 times 1, 3? Now look at this matrix, 1, 1, 1, 1. It squashes the unit square into a single line. Area 0, determinant 1 minus 1, 0. Singular, 2 tools in 90 seconds, matrix times vector, and the determinant. With both in hand, you're ready for the recipe actually finding eigenvalues. Finding eigenvalues isn't magic, it's just algebra. 4 honest steps. 1. Write down the matrix. 2. Set det of A minus lambda I equal to 0. 3. Solve for lambda. 4. Take each lambda back and find its direction. 4 steps. That's the whole exam question. Start with AV equals lambda V. Subtract lambda V from both sides. But wait, lambda is a number. A is a matrix. The types don't match. Here's the fix. Remember the identity matrix I times any vector is that vector. So lambda V equals lambda IV. Now the subtraction is now factor out V from both terms. A minus lambda I all times V equals 0. That's the equation we solve. Every eigenvalue problem in the world starts right here. Quick, before we go on, why must V not be 0? Think about it for a second. The answer unlocks the whole derivation. If V were 0, every lambda would work. Every number would be an eigenvalue, and the word would mean nothing. So V must be non-zero. And then this matrix has to send a non-zero vector to 0. Here's what collapsing space actually looks like. Take the matrix 1, 1, 1, 1, hit any vector with it. Every result lands on the line y equals x, and watch the grid flatten. The area goes to 0, and its determinant 1 times 1 minus 1 times 1 is 0. Singular means collapse. Collapse means determinant 0. So det of A minus lambda I equals 0. Our matrix is 2, 1, 1, 2. Its determinant 2 minus lambda squared minus 1 equals 0. Expand it, lambda squared minus 4 lambda plus 3 equals 0. Now factor. What two numbers add to 4 and multiply to 3? 1 and 3, so lambda minus 1 times lambda minus 3. Check it by the eigenvalues are 1 and 3, two numbers, and each one now needs its own direction. Want the 3x3 version? Comment 3x3 and I'll make a whole episode. Step 4, each eigenvalue gets its own direction. For lambda equals 1, A minus I is 1, 1, 1, 1, the exact singular matrix we just met. Solve it, x plus y equals 0, so y equals negative x. Pick x equals 1, then y equals negative 1. The eigenvector is 1, negative 1. Verify A times it gives exactly 1 times it. Now lambda equals 3, A minus 3, I is negative 1, 1, 1, negative 1. Solve it and you get y equals x. Pick x equals 1, so y equals 1. The eigenvector is 1, 1. Verify it. A times it gives 3 times it. On the plane 1, negative 1 keeps its length. 1, 1 triples. And look, they're perpendicular. Two directions, infinitely many vectors. That's the answer to the opening question. And here's the whole idea in one sentence. An eigenvector is the direction that survives, and the eigenvalue is how much it stretches. Stay tuned at the end. There's a one-line shortcut linking eigenvalues to the determinant. You've found them, the directions and the numbers. Now the question that actually matters, why should you care? Because this isn't just textbook algebra. Eigenvalues quietly run the modern world. Okay, why should you care? Here are 3 places where eigenvalues quietly run the real world. 1. Google. The original PageRank modeled the whole web as one giant matrix, and the most important pages, they come from its principal eigenvector. The principal eigenvector is the one with the largest eigenvalue. It points to the most important direction. This one equation ranked the internet. 2. Everything that vibrates, every bridge, building, and airplane wing, each one has natural frequencies, and those frequencies, they're its eigenvalues. The shapes it vibrates in are its eigenvectors. Engineers compute these ahead of time, so the bridge never shakes itself apart. 3. Data, PCA. Principal component analysis finds the directions where your data spreads the most, and those directions are eigenvectors of the covariance matrix. The covariance matrix captures how data spreads in every direction. Its eigenvalues tell you which direction matters most. Quantum mechanics, facial recognition, recommendation systems, same equation. One equation, AV equals lambda V, holding up every single one of them. Now let's lock in everything you learned, and then one last secret. The whole journey. An eigenvector is the direction that survives. An eigenvalue is the stretch factor, and det of A minus lambda I equals 0 finds them both. Two directions, infinitely many vectors. Remember that one direction that refused to rotate? Now you know exactly why.